How do AI systems understand meaning instead of matching exact words? How do they find relevant information across millions of documents instantly? They do this using vector embeddings that represent semantic meaning numerically. These embeddings place ideas inside a high dimensional mathematical space. But embeddings alone cannot support real AI applications at scale. They also rely on vector databases that search these embeddings efficiently. Vector databases identify the closest information using powerful similarity metrics. These retrieval steps supply context to generative models during RAG workflows. Today we will explore embeddings, vector databases, similarity models, and RAG systems. Embeddings convert text or images into numerical vectors representing meaning. These vectors help AI understand concepts beyond exact words or phrasing. Similar ideas generate vectors that appear closer together in vector space. For example, customer support aligns closely with help desk due to shared meaning. This closeness reflects underlying semantic relationships between phrases. Embeddings act like coordinates that place ideas in semantic space. Embeddings live inside high dimensional mathematical spaces with many learned features. Each dimension represents a feature extracted from training data. More dimensions allow richer semantic representation but require more computation. Embedding models use neural networks trained on massive datasets. These models learn context, relationships, and intent encoded within text. They transfer human language into machine friendly numerical structures. Embeddings allow AI to perform efficient semantic search. They perform models compare meaning rather than match keywords. Vector databases store these embeddings for fast and scalable retrieval. Now let's see how these powerful embeddings are actually created. Embedding models are neural networks trained on very large datasets. They learn patterns from how words or images appear together. The model converts each input into a fixed length numerical vector. Each vector dimension represents a learned semantic feature. More dimensions capture deeper relationships and richer context. However, high dimensionality increases computation and storage requirements. Training adjusts network weights to improve semantic consistency. The model ensures similar inputs generate consistently similar vectors. Different embedding models specialize in different tasks or modalities. Some focus on text, while others focus on images or mixed inputs. Developers choose models based on accuracy, latency, and hardware limits. Smaller models run faster but capture less nuance. Larger models capture subtle meaning but need stronger hardware. Embedding creation happens during data ingestion or real time processing. Good preprocessing ensures clean, consistent, and reliable embeddings. Embedding models find patterns learned from massive training text. Consistent preprocessing ensures more stable and comparable vector outputs. Next, let us understand how systems measure similarity between embeddings. Vector distance metrics measure how similar two embeddings are. These metrics guide vector databases during similarity search. Different metrics work better for different data types or tasks. Cosine similarity is the most common choice for text embeddings. It measures the angle between two vectors in semantic space. A smaller angle indicates higher semantic similarity between vectors. Cosine similarity ignores magnitude and focuses on direction. This makes it excellent for documents with varying lengths. Euclidean distance measures straight line distance between vectors. Smaller distances indicate more similar content or features. Euclidean distance considers both direction and magnitude together. It works well when numeric values carry meaningful semantic information. However, Euclidean distance struggles in extremely high dimensional spaces. Dot product combines angle and magnitude into one similarity score. Larger dot product values indicate vectors pointing more similarly. Dot product often favors longer or denser vectors. It is useful when magnitude reflects content intensity or importance. Choosing the right metric strongly affects search accuracy and performance. Wrong metrics can reduce retrieval quality significantly. Metrics also influence computational cost during large scale searches. High dimensionality can distort distance calculations drastically. Developers test metrics to match real data characteristics and needs. Let us compare vector databases with traditional databases to see key differences. Traditional databases store data in structured tables with defined schemas. They rely on rows and columns for organization and retrieval. Vector databases store high dimensional vectors with associated metadata. Their structure is optimized for mathematical similarity search. Traditional databases use exact matching through SQL queries. Vector databases perform nearest neighbor search based on semantic similarity. This allows retrieval based on meaning instead of keywords. Keyword matching fails when users phrase ideas differently. Traditional databases excel at transactions reporting and structured workloads. Vector databases excel at unstructured or semi structured semantic retrieval. They use indexes like HNSW or IVF for fast similarity search. These indexes speed up large scale approximate nearest neighbor retrieval. Approximate search sacrifices small precision for massive performance gains. Traditional databases guarantee accurate and deterministic results. Vector databases prioritize speed and scale in large vector spaces. Traditional systems scale differently than vector systems. Large relational queries often slow down under heavy workloads. Vector databases maintain sublinear query performance at scale. Traditional databases suit transactional and operational applications. Vector databases suit recommendation systems and semantic search applications. They power chatbots, AI assistants, and enterprise knowledge systems. Vector systems enable AI to understand contextual similarities deeply. Vector databases shine when meaning matters more than wording. Developers choose systems based on workload, data type, and retrieval needs. These architectural differences shape how modern AI applications are designed. Now we can explore how these technologies power modern generative AI. Modern generative models gain power from external knowledge retrieval. They use vector databases to access relevant information instantly. Retrieval-Augmented Generation forms the core of this approach. RAG retrieves context before the model generates a response. This grounds the model's output in factual and relevant information. RAG significantly reduces hallucinations by supplying verified context. Developers update knowledge bases without retraining large models. This makes systems flexible, maintainable, and easier to scale. User queries are first converted into vector embeddings. These embeddings are then used to search vector databases. The system retrieves the closest matching content quickly and efficiently. The model uses this retrieved content to produce accurate responses. RAG improves accuracy in enterprise, technical, and real world applications. It supports fresh, dynamic knowledge without ongoing fine tuning. It forms the backbone of many reliable AI assistants today. Let's look at the architecture supporting effective AI knowledge retrieval. A robust knowledge base ensures effective retrieval for generative systems. Content is collected automatically using ingestion pipelines. This content is divided into smaller, meaningful segments for processing. Chunking improves retrieval accuracy and model comprehension. Chunking breaks document into retrieval-ready semantic units. Each chunk is converted into an embedding vector. Metadata is stored alongside each vector for filtering and ranking. Metadata improves filtering and speeds up targeted retrieval. Vector storage scales independently from other system components. Retrieval APIs process semantic queries with low latency. These APIs return the most relevant vector matches instantly. Models use these retrieved chunks to generate accurate responses. Systems must balance indexing speed with retrieval precision. Good architecture enables fast updates without disruption. Scalability is essential for large enterprise knowledge bases. Independent scaling prevents bottlenecks during heavy workloads. Proper preprocessing greatly improves retrieval quality and consistency. Now we will see real engineering examples using these technologies today. Vector search powers modern code search tools effectively. Developers find similar code snippets through semantic retrieval. Documentation search becomes easier using vector based matching. Users get relevant answers even when queries are vague. E commerce platforms use embeddings for product recommendations. Similar items are identified using vector proximity. Media apps recommend songs or videos using vector similarity. Customer support systems match questions to past solutions automatically. Chatbots retrieve helpful articles using semantic search techniques. Security tools detect abnormal behavior through embedding comparisons. Fraud systems identify unusual patterns using vector distances. Enterprises build internal RAG systems for knowledge access. Employees query unified knowledge across multiple data sources. Healthcare systems retrieve similar medical cases using embeddings. Education platforms recommend learning resources based on semantic understanding. All these applications rely on semantic similarity and fast retrieval. Let's wrap up everything we learned with a quick summary. Embeddings help AI understand meaning beyond exact words. Vector databases enable fast and scalable semantic retrieval. RAG combines retrieval and generation for highly accurate responses. These systems reduce hallucinations and improve reliability significantly. Modern AI relies heavily on these retrieval pipelines. Understanding these components makes you a stronger AI engineer. These skills open doors to modern AI engineering roles. Keep learning to build more capable AI systems. Thanks for watching and subscribe if you want more AI learning resources.